5.2. Where it should be maybe the closest Clapeyron formula or equation should be stated this way: the log of some normalized pressure, okay, should be proportional to minus 1 over T, where T is in Kelvin, degrees Kelvin. Okay, and P nu star is some constant times P nu, okay, for some constant. All right. So that means really what you have is that the log of P nu is a linear function of 1 over T. Okay. And not necessarily with slope. Let's see, is this, he's got it with slope minus 1. Oh no. Yeah, so he's got, so then he's got, yeah, so that would mean that log of P nu star is some other constant, C1 minus C1 over T. And that would mean that the log of P nu is equal to minus C1 over T plus some other constant, C2. All right? So really what it means is the log of the pressure is a linear function of 1 over T in the pressure units that he's giving. Okay? So there is an intercept, is the point. There is an intercept. So there was a correction to the way it was stated. So without the star, it was incorrect in his units. All right. If you change the units, then it's correct. Okay. Where there was the vapor pressure, that's the I guess the V was, or nu was for vapor. Okay. Anyway, I don't really understand the equation that well. It has something to do with vapor pressure of things that are below freezing. Okay. Okay. So 273 degree Kelvin or something like that. It's normalized around 273 Kelvin, which is 0 degrees centigrade. The formula, if you look it up on the internet. Okay. Okay. So what the first couple of problems in Chapter 5 are about is you can have regression equations that aren't linear functions, okay, of the natural regressor, but can be maybe transformed to be linear, okay, by transforming y or x or what have you. Okay. So, is everybody happy with that? That you can handle these problems? And if I have exponential growth or decay, if I've got y equals beta 0 e to the beta 1t, okay, then I can transform that simply by taking the log of both sides. You take the log of y is equal to log of beta 0 plus beta 1t. Okay? So if I have an exponential, so this is a case where the equation is transformably linear. Okay? In some sense. At least by transforming the y variable. Okay. Here, of course, would you have additive errors? If I had additive errors here, then it doesn't really, then the log of a sum is not the sum of logs, so I don't get additive errors over here. So it's kind of natural here to have the multiplicative error, all right, times 1 plus epsilon or something like that, okay, the multiplicative error. Then you get plus log of 1 plus epsilon, which roughly behaves like epsilon, okay. So I'll just make that one comment, that if you do have an exponential model, what have you, then if you want to get to the standard assumptions, you better be considering multiplicative errors here. Okay, otherwise this transformation doesn't do you any good. Or it doesn't help that much. In practice, you can do it. But you still have to look at the residuals and so on. How is your model working? So if you just take the log of the regression function and get it to transform, okay, great. But what about the errors? You know, did they transform as well in the right way? Okay. Okay. So he's pretty much in this part of the beginning of chapter 5 just saying, think about only the regression equation. How would you get it to transform? Okay, don't worry too much about the errors. You'll have to study the residuals anyway. Okay. So what people will do in order to use linear regression, right? Because it's such an easy thing to use. Okay, it's such a so wonderful. Okay, so let's see. I have a couple comments about chapter 5 before we go on, and that is on the weighted. I think I did mention last time that I was going to do the Poisson example 5.1 by weighted least squares, and so I thought I'd show that before we go on. So let's just have a look at that. There was just maybe one little subtlety that I'd mentioned before we go on with the numbers. Because there, when you transform, well, we did it in the example 5.1, we took not the log, but the square root of y. And so let's have a look at that again. What we did is we... I don't know what's going on here. We had peak energy usage was the y variable, and overall energy usage for the day by a customer was x. Okay, and we had the scatter plot y versus x, and we had the funnel-shaped residuals for a simple linear regression of y on x. Okay. So, and we tried a square root transformation. We did use it, and so on and so forth. Now, this is the weighted approach. Why am I looking at the weighted approach? I want to look at the other one. This was the original one. This is with the y stars. Okay. Again, and then I put y star as the square root of y. It's the same scatter plot here, but this was the scatter plot of y star versus x after I took the square root. Okay, and then I applied simple linear regression. We got some coefficients to estimate y star. Okay, now how do I estimate y? Well, what I said was I could just take my y star hat, right, and square it. Okay. And that would be an estimate of y. Now what happens now? I could call it E tilde now is y minus y hat squared. What do I get when I actually sum the squares there? Sum of the squares of the E tilde is 124.3971 versus the sum of the squares with the best linear fit is 126. Now how can that be? How can I get a smaller sum of squared errors? I'm approximating one column by another column. So what conditions on that other column makes it the best fit that I get to 126.87 is the error sum of squares? Remember your theory now. I'm getting 124. I'm getting a number less. Sum of the squares of the E tilde is 124.4 versus 126.87. Okay? Let's see what I wrote here. Note that the sum of squares of E tilde is less than 126.87 for the SS res than the original simple linear least squares fit. Okay? This is possible because the column y star hat squared is not a linear function of x. It's beta. It's some I call it beta star 0. Beta 0 star hat plus beta 1 star hat, okay, x squared. Okay, that's not a linear function of x anymore. Right? It's a quadratic function of x. Right? It's some quadratic function of x. So it's actually, since there's only two parameters, well, anyway, it's not a linear function of x. Okay? So that means I can actually get, so in other words, the 126.87 is the minimum error sum of squares under all possible linear fits to the data. Okay? Well, this is a nonlinear fit, so I can get a smaller sum of squares. Okay? Okay? One other comment, though, is that here the transform model assumes that the e of the square root of y is beta 0 star plus beta 1 star x. Okay? So these estimates up here were, I called them beta stars because it was a transformed y star values. So these I called beta 0 star hat, beta 1 star hat, putting an extra, asterisk on there to show that it was for the transformed data, y star on x. Okay? Yes?
Would that have been a larger number?
What larger number?
If, for example, the sum square of the e tilde...
Okay, this had been bigger?
That would have been a sign that this new fit was even worse than the linear?
Yeah, it would be worse, but with a nonlinear function. So, I don't know, that would have been some indication that it wasn't great, unless it was not very much worse. Okay? Now, I'm going to have a weighted least squares approach where the sum of squares errors has to be bigger. But it's still going to be a linear function that I'm approximating with. Okay? But the whole point is that the stability of the estimates. Let's see if I can remember this over here. In the simple linear regression fit, what do I have? I've got the coefficients are minus 0.831 and 0.0037. Those do give an unbiased estimate, for the expectation. Okay? In other words, if I take beta 0 hat plus beta 1 hat x, I get a straight line, and that gives you predicted values which are unbiased estimates of the actual mean. All right? But because the variance is not constant, actually, those estimates, though they are giving unbiased estimates through the predicted equation for the mean, given x, they don't have the small variances and so on. Okay? They don't have the minimum variance property because the variances are not equal. Okay? They don't have the minimum variance property. Here the standard errors are 0.0003. Maybe we should put another digit on there. 334. Okay? And 0.441. P-values, this p-value is not that small. 0.065. The intercept. Okay. All right. So I'm just pointing that out that the normal probability plots for what? What was that? A normal probability plot of? Normal probability plot of residuals of transformed data. That looked okay, roughly speaking, except that we mentioned there was this one outlier in this energy data. Okay? Apparently. Okay. So the transform model assumes that the square root of y has the mean beta 0 star plus beta 1 star x. And so therefore I get unbiased estimates for the expected of the square root of y. Okay? However, it does not follow that the expected value of y is in fact equal to the square of this mean. Okay? And, okay, so at the beta star level I do have an unbiased estimator, but there is a bias, okay, when working with the original units, as I mentioned above. There is a bias for this square estimating beta 0 and so on. So in fact, and also there's a bias for estimating EY, because this is not the same thing as EY either. Okay? Okay, it's a little confusing, but so the author, when it came to all this, because there's a lot of things going on, it just kind of just sweeps it under the rug a little bit and says, well, okay, there's something going on here. Let's not worry about it too much. Just go on to the next example, okay? This gets a little off into the ozone there. All right. No, what I wanted to look is the weighted version of this. Okay, so I wanted to remember what my least squares estimates were. My least squares estimates were down here. Okay? Those are my least squares estimates. What about the weighted case? How can I approach this by a weighted case? Well, I know that my model is that it is Poisson data, so that the variance should be equal to the mean. So my alternative is, I'm still making the same assumptions, why not do it a different method? Same assumptions. Okay? Then I can still get, what do I get? Then I can at least get the mean unbiasedly. Okay? The mean of y unbiasedly this time, if I use the weighted least squares. All right? And so what I get is, let's see what I had, a 0.003 before, 0.0037, and now 0.00357 for the slope. Okay, the intercept before was negative 0.831, now it's negative 0.708. Okay, this is a weighted least squares approach. So what did I actually do? I took W as 1 over y hat. I took this simple linear regression to basically figure out about how big the mean is. What am I going to do? Okay, so it was a linear increase of peak usage. Okay? Take 1 over y hat as because y hat should therefore be about the mean, and the mean is the variance. So W is 1 over the variance. Okay? Then I take the square root of W times x, square root of W times y, the usual thing. I take the no-intercept regression of this square root of W times y on these two columns. Okay? There's a no-intercept regression. That's what I got here. Okay? And so I got my beta 0 hat and my beta 1 hat. Now I plug those in and go ahead and get my predicted values in the original units. Okay? Where are they? Over here. I go ahead, well, I actually did a second weights, because now I have a new formula for what my y hat is, because I have new beta 0 and beta 1, so I went ahead and did a second iteration. Okay, and I didn't get much change at all. Okay, and then I went ahead and I calculated then, even after all that, I calculated my y hats, and therefore my residuals, which would be y minus y hat. A03 was my y. Here's A03 right there. A03 was my y. I copied my y over. So my y minus the y triple hat, which is my formula for y triple hat, was to go ahead and take the last beta 0 I got in here. This was AX19. Does that look right? AX19 right there? Okay. And my AX20. All right, and I had to freeze them when I put this formula in. Okay, so those are my. So that's my least square fit now. All right. And now I get my E triple star. And now I get my means. The sum of the squares of those turns out to be, here they are. SS res triple star original units 127 versus the original one, which is 126.87. So I have to get a larger SS res from them, because it is a linear fit now, right? But the point is that, okay, what did I want to look at? The properties estimates. Okay, now a p-value of 0.018 and a p-value 10 to the minus 14. Okay, for the two estimators. Okay, so they're much higher quality estimators. Okay. Yeah, you look at the standard error of the slope. It's down by 0.00033. I don't know. I can't remember what the other one was. Was that much different? And 0.00334. I guess they're about the same. Okay. I guess the intercept is the only one that really got improved here. Okay. Anyway, that's the weighted least squares approach. The data. Okay. Questions about this? So it seems like it wasn't that big of a difference, okay, between the Poisson approximation, between taking a square root and not taking a square root, all right, in this case. But there's the technique, all right? iterated least squares. Weighted least squares. Okay. Okay. Let's go on. What are we going to do in Chapter 6? I'm going to take a quick hit on Chapter 6, then we're going to go into polynomial regression in Chapter 7. Okay? Chapter 6 has to do with we already talked a little bit about leverage and influence in that modified Anscombe's data. And I think I even refer to that in these notes. Here's a few notes today. Okay? Go ahead and hand those out. What we're going to do is introduce a bunch of diagnostic measures for seeing whether a data point is a leverage point or an influence point. Mostly our focus is on influence. He has two definitions though. One is influence and one is leverage. What's the definition? So he tries to make it as clear as possible in this chapter what the definition of leverage and influence is. And it goes like this. A leverage point is a point A definition. A equals xi1, xi2, xik, comma yi. That's the point in the scatter diagram, right? And he shows you a picture in the book in the just in 2 dimensions. Is a leverage point if xi1 through xik is remote in X space. Okay, whatever that means. It means it has a high HII value. Okay? Okay? But he's saying it's a leverage point, okay. So it has unusual X value. I think I might have said something in my notes a little bit different. He tried to make it, and he said, but it wasn't really clear, such that the original data point A lies nearly on the regression surface determined by the other points is the example he's showing. So the leverage point may actually not control key properties. So this is just a leverage point if it's remote in X space. Period. Okay. So I think I made a mistake in my notes by kind of misinterpreting what he said. Let's put it this. Let's write what he wrote. Read what he wrote. Excuse me. Consider the situation illustrated in the figure 6.1. Might as well just show a picture of that. 6.1 is you've got a bunch of points in a scatter diagram, and then you've got one that's further away in the X space. But the point A is not far away from the regression line that would be determined by the other points in this plot. Okay. All right, that's the situation illustrated. Nevertheless, you call that point A leverage point because the X coordinate is remote in X space. Okay. So, depending on whether there's an unusual Y value with respect to the rest of the data, it may control certain model properties or not. Okay. And then he goes on and says, now if on the other hand, an influence point is one that is has leverage plus an unusual Y value. Okay. It's not a very clear definition. I mean, it's not mathematical, right? This is not a mathematical definition. I tried to make it as mathematical as possible. What he's trying to say here is that leverage means that if you repeated the experiment, right, and then you got an unusual y value, then it would become an influence point, right? But as it is in your data, the point has potential influence, okay, if it doesn't have an unusual y value. So we call it a leverage point.
Is it like an outlier?
You could say it's an outlier in the X space, okay? But there's no but you don't get a large residual from that leverage, from the leverage point example he's showing. But just think about it in repeated experimentation with the same X values, right? The same X values in your data. Then you might, instead of getting the point that lies out here, okay, that lies on the line, or roughly close to the line, it might drop down or something like that because of certain variability, right? And then it may change the slope and intercept of that line quite a bit. Okay, so on repeated experimentation, all right, it exerts a lot of influence. Okay, though in your particular experiment, it didn't exert any influence at all because it already lied on the line determined by the other points. Okay, an influence point, on the other hand, is one where indeed there is some leverage associated with the point, and in fact it exerts the leverage. Okay? Did you exert the leverage or did you not exert the leverage? But it's a leverage point nevertheless. So leverage simply means remote in the X space, corresponding to a large HII value, and influence corresponds to having leverage and exerting the leverage. Okay? That's pretty much it. Now, outliers have to do with large residuals where you're not in remote in the X space. Okay? Just per se. Now, if you could be remote in the X space too, but then you wouldn't expect a very large residual. That would be very uncommon because if you're very remote in X space, the line or the surface is forced to go near that point and keep the residual small. Okay? So influence is the key word. It's probably more important than studying outliers in some sense. If there's a point in the middle of the data set, like up here, okay, that's sticking above this cloud of points here, okay, it's not going to control it's not going to, because it's just not that far. It's going to affect this line somewhat, and it will. Okay, definitely. Okay, but not if this other one is sticking in there. This one's still going to make it go over there. Okay, because I can't make this one go over here because then that's going to be big. Okay, so then outliers do exist when you get a large residual. Okay, but it's certainly not going to be for a point. A very large residual is not going to be for a point remote in X space. Okay, it can't happen. By definition, the least squares process. See what I'm saying? I mean, there's some intermediate cases we're not worried about, but that's the definition of leverage and influence. So what are some measures of leverage we already had? The HII. So HII equals the diagonal element of the hat matrix, capital H equals X prime X inverse, X prime. And there is a way to get it with Excel, apparently, because some Excel people responded to Joe on the email or internet and found a way. Okay? And so we may investigate further a little bit about that. We know how to calculate H by using array formulas. And so we can find the diagonal elements at least as numbers. Okay? And then trying to get them moved into an array is the problem. But apparently it is possible. There's enough enough power to do with Excel. Someone has the power, as Joe said. Okay, so And what we know is that the trace of this H matrix is what? This is an n by n matrix. But the trace of this n by n matrix is P equals a column dimension of X. Okay? We're assuming that X had full column dimension. Okay? So that it was the X prime X would be invertible in the first place. Dim X equals P. Okay? So so there's sort of an average value. Therefore, the average value, HII bar, so to speak, would be P divided by N, because there are N of them, right? So a cutoff value for a large HII would just be twice this number. It's kind of a traditional value, okay, that people came up with. Okay, so HII large would be HII bigger than 2P over N. So you kind of, to flag whether there's a leverage point in X space, right, whether the XI1 through XIK is remote in X space, you look at, see whether HII is bigger than 2P over N. Okay? And then you put a colored box around it, around that observation number. All right? Okay, what are some other possibilities? That's for leverage. Now, what about for influence? Well, I did give an example of this, large HIIs in the delivery time data. Okay? I think some obvious ones were observations 9 and 22 in the delivery time data. Okay? I could pull up the delivery time data, but I don't think I have it fully analyzed. Let me see if I've got anything. We didn't... soft drink data. Let's see what I do with anything with that. I didn't do much with it. Oh, let's see. We did do some calculation with that. We didn't calculate the H matrix, though. That wouldn't be too difficult to do so. I called it W. All right. Oh, I guess I could show it then. Okay. Delivery time data. What was this? Okay. This was to multiply F13 through H13 F8, H10, transpose F13. What is F13 to H13? Oh, it was this one. Okay. Yeah, this was a certain 1/8-1200. That was a particular, that was the problem of, I want to change these numbers, right? If I want to find the input for observation number 9 in the delivery time data was, let's see, it would be down here. It would be, so it would be X1 equals 30 and X2 is 1460. Let's change these numbers right here to 30 and 1460. That should change everything. Oh yeah, it did. Okay, so there's the I think that's the largest HII for the delivery time data was 0.49829. Okay. I don't think I have this on the website, this particular document, but it's kind of our running example through the book. So what I did is I took this row times X prime X inverse times the transpose of that row, and I got 0.498. That's an HII. This is H99. Okay? Maybe I should put commas there so it's not H. Yeah, I do. I need, because it was the IJ entry. Okay, something like that. Okay. So, what if that's a large one, right? Because what is 2p over n in this case? P is equal to 3. There's 2 regressors, 3 columns of the X matrix. Okay? So P is 3. N is 25, I believe. 2 through 26. There are 25 observations of delivery time data. Or you can see it up here. Here's the 25. So what's 2 times 3 over 25? The 6 over 25, that's 0.24. That's 2p over n. So 2p divided by n equals, oops, what happened there? Equals 2 times 3 divided by 25, and I get 0.24. So this is bigger than 0.24. So observation 9 is the leverage point at least. Okay?
We do have the H matrix for that.
Yeah, we do have the 8 from notes 3. Notes 3 has the full H matrix. You've been using that. Okay. So this does show that this is the maximum HII, I believe. Yeah. Now, what happens if you take observation 9 out? Right. What happens if you take observation 9 out? How come I can't change it? What do I want to do? I just want to customize. I just want to change it to a different color. How come I won't do it? You want a different toolbar? Oh, I just want it to go like this. I see. Format. Yeah, there you go. Font, color, patterns, whatever. Here it is. Okay? There they are. Okay, there's observation number 9. Okay. So, now I'm going to take it out. All right, so I need to copy and paste this thing, and I want to see what happens to the least squares estimates. Did I have least squares estimates before? Yeah, I did. No, I didn't. I never calculated the least squares estimate, so I guess I better do that first. Okay. So let's do that. Tools. Data analysis. Regression. Okay. Input Y range was all of these, right? Okay. Input X range was just the X1 and the X2. No column of ones. That was only used for calculating the X matrix. Variables, yes. No constant. No. Okay. Output range. All I want is the estimates. Okay. So we get beta 0 hat, beta 1 hat, and beta 2 hat. Okay. That's with a full data set. Okay? Then we go ahead and take that observation number 9 out and see what happens. Is it an influence point? Okay? We know it's got a leverage point, but is there influence there? And so we have other diagnostics for that, but let's just go ahead and do it by hand. So now let's take the observation out. So copy this whole thing down. See, I keep it on the same level over here. Paste. Okay, now take this out. So how could I do that? Yeah, that's true. I could do that. That's easy enough. Because Excel is automatic enough. Yeah, it said up. That's good. All right. So now, do the same regression problem. Where do we go? Okay, this is kind of mundane, but anyway, sorry, it was taking the time to do it, but let's just go ahead and put this in. And output range. Let's put it down right next to these other ones so that I can compare easily. I should just write over this stuff because I don't need those confidence intervals. Okay. So now what am I getting? I'm getting these. So let's compare those two bolts. These bolts versus those bolts. Okay, the intercept changed dramatically by almost a factor of 2. And the other two coefficients didn't change that much. Okay, the second coefficient changed a little bit. Now, is this fitting what's going on in Chapter 6? Did he give the same information? I took 9 out. Yeah. Yeah, it looks like this is the same information. So he's got a 0.01498. It's his beta 2 coefficient. I got 0.01438. Okay, so I don't know. That's a typo somewhere. Okay? If people are typing these things in, 616, that looks the same. So somebody, this is again another data transmission error right there. Okay. I guess that wouldn't happen today with everybody cutting and pasting all the time. This is still in the old days. Okay? When people type these things in. Okay. So, okay, so it was influential on beta 0 and somewhat on beta 1. But what's our measure of influence? Do we have other diagnostics? Could we have told that without having to do this whole regression again? And it turns out we could have learned some of that. All right. Any comments about that? So let's look at some of these other measures of influence and go through the formulas just a little bit. Well, we're running out of time. I wanted to get one more web page too. One more Excel sheet. One more worksheet. Okay. So what I want to do is consider, we already talked a little bit about this, but one of them is, okay, Cook's D. So we're going to have as a deletion measures. What we're going to do is we're going to delete the ith observation. So delete that leverage point. Okay? Is that going to change anything? If it's merely a leverage point and not an influence point, okay, then the beta shouldn't change, right? And your predicted value y hat sub parenthesis I wouldn't be any different, okay? So you've got y hat I and you have y hat deleted I, all right? ith observation deleted. If there's no influence, these should be about the same, okay? So what I'm going to do is to check to see if there is some influence. I'm going to calculate something called di, which is simply x times beta hat minus x beta deleted hat. Okay, so I can also come up with the betas when I delete the ith observation, right? Norm square, take the square of the length of that vector and divide by p ms res. Okay. What is this thing? This is actually nothing other than y hat minus y hat deleted I. Okay. Those are columns, right? Excuse me, what I mean. Well, yeah. I've deleted as a vector, okay? Norm squared divided by p. The notation is a little bit complicated. Because by this thing you think of the deleted value of y hat at the ith value. So I can actually put another I there. Okay? But I can still talk about the whole vector of deleting the ith observation of the y hat vector, right? That's what x beta I is, okay? So this is really the whole vector, okay? Versus just the one observation at the ith point, okay? So I can talk about this at the ith point, So that's whether the predicted value at observation I changes much compared to these two, right? Then I also have just the whole vector. Put this deleted I notation in there. You making sense? Okay. That's the Cook's D. What we know from before is that this thing, we know page 105, that x beta hat minus beta, if I take the norm square of that and divide by p ms res, okay, then this is actually distributed as an f random variable of p and n minus p degrees of freedom. We didn't go through the distribution theory to prove it. Okay, so it's the same thing. All I'm doing is factoring it, but I'm replacing the beta hat sub I by the beta. So this is the actual vector of parameters. We know that. So that means, so the real question is how much is beta hat being changed by when I delete the ith observation. That's Cook's D's. The question posed by Cook's D essentially is this beta hat far from this beta hat, or is this vector far from this vector? Okay. Well, because this is true, all right, then when I delete the ith observation, if this is very large, then that puts beta I hat at the boundary of a confidence region for beta. Okay, this defines the confidence region for beta. If you recall how that goes, I say this less than or equal to f.05. All right, gives a region, okay, of beta space, okay, which has the center. It's an ellipsoid which has center at beta hat. Okay, and so you've got this business. You've got beta hat in the center, and you've got this confidence region for beta. Okay, and I could say if I take x beta hat minus beta norm squared divided by p ms res, and I say that's less than or equal to f, let's just make a 50% confidence interval for kind of a, then this is a 50% confidence region for beta. That's as a function, this is on the beta axis, beta 1 and beta 0, beta 1 are the variables in the case of simple linear regression. And beta hat is equals beta 0 hat. Beta 1 hat is the center of this confidence region. Okay? So we'll say that, okay, there's a 50% confidence region. Well, okay, that's not a very high confidence, but it's kind of a, sort of a middle of the road place where I expect beta to be. Okay, now if beta I hat is on the edge or outside of this region, okay, we'll say, well, that's a kind of a big change. All right? That's kind of the idea. So what we're going to do is we're going to take f, we're going to say d should be less than or equal to 1 because f.50 is roughly 1. That's a middling value of the f distribution. So we'll say di is large if d is bigger than 1. That's the point of this normalization. Okay? This PMS res in the bottom. Okay? So di is big if di is bigger than 1, since f.50 p n minus p is roughly 1. Okay? So that's Cook's D. Now there's a nice formula for Cook's D because you don't want to have to calculate that, right? And there's an appendix C8 where he actually has one key formula. Now you went through some of the formulas in this page. I'm not going to be able to go through all of them today. And the key formula from appendix C8 is that beta hat minus the deleted estimate of beta is equal to x prime x inverse times the column vector x1 x xi1 down to xik. It's a column of p terms, all right? And then times ei over 1 minus hii. These are just scalars at the end. Ei is a scalar. 1 minus hii is a scalar. Okay, that's the key formula that takes a bit of work to get. All right, but once that's obtained, everything else in this chapter, all the other little formulas, practically speaking, derive from that one. Okay, and so it turns out that except for this H matrix, all the except for the computation, all the difficult computations doing this deletion thing boils down to finding these H's, these HIIs, because everything else can be written in terms of them, as we'll see. Okay, so I think then we get the Cook's D, and then we have something called, I'm not going to be able to do the DF betas today either. So what is the Cook's D? And then there's two other things. Maybe I'll just mention the DF fits, because the DF betas I'm not going to be able to do right now. What's DF fits? DF fits. I think the DF, you're going to see this DF coming in. Where's that coming from? Deleted fit, I think is what it stands for. That's my best conjecture. I don't know. The author doesn't tell what the DF stands for. Deleted fit fits. So full of fits. Okay, what is that? That is defined to be yi hat minus y hat I at the ith deletion. Okay. Divided by S. You take the estimate of variance where you delete the ith observation. That's usually not that big of a deal, but it does sometimes get a little bit changed, okay? Because you're changing the number of degrees of freedom in it anyway, okay? And then your HII there. What would that be? This is the number of standard errors that yi hat changes by when we delete the ith observation. And you say, well, why didn't they put a sigma hat in here, a sigma hat squared instead of the SI squared? Well, that's just to accentuate it a little bit, the SI squared. Throw that in there. 1 minute? Yeah. Oh, I do. Okay, that's because the variance, since the variance of yi hat is HII times sigma hat squared. Okay, that's what it. Sometimes sigma squared. Okay, so that's what it is. So that's why I'm dividing by the square root of HII times sigma roughly. Okay, divided by the standard deviation or standard error. So it's a number of standard errors. So I'm putting this extra I in here. So that's what the deleted fits thing is. And then they have a cutoff for that. And they don't really motivate the cutoff for that. I think the cutoff for that is 2 times the square root of p over n. That's the suggested cutoff. Okay, let me look at one these things. Okay, it's called what is it called? The wine data. Exercise 612. Let's see what I've done here. And you can sort of copy what I've done when you get to this exercise. You have to deal with the house data. Or property valuation data. You're going to do that for your test, and you're also going to do it for your homework due the day after the test. Okay? So maybe you'll get a head start doing the house data on your homework. Okay. What I've done here is taken a data set from the index and see there was quality of wine, and there were 5 variables: clarity, aroma, body, flavor, and oakiness. I don't know who rated these things or what have you, and it was the overall quality of the wine. Okay, then there was the region it came from. That regressor is not being used in this particular analysis. Okay, so region is not being used in this one. As you can see from when I do this, the multiple regression, there's no region in there. Okay, full data set, intercept, clarity, aroma, body, flavor, and oakiness. Okay, and there's the residuals. Okay, versus the predicted value. Okay, all right. So the question is there any leverage or whatnot in here? So what I've just gone through and highlighted the points that had leverage, okay, by eyeballing and see whether the cutoffs were exceeded, okay? You can do it automatically too, I suppose, all right? And then I've also looked at, for example, Cook's D. What happened to Cook's D? None of them are exceeded. None of them are bigger than 1, okay? So in some sense, in the average sense, the betas weren't moved that much. Okay? So the Cook's D is an overall average where all of the betas moved sort of in an average sense. Okay? However, individual fits were changed a lot. Okay? The cutoff was 0.795 according to the little gizmo they gave in the text. That wasn't motivated that well. I haven't looked up the research on that, so I'm going to skip that for now. I can probably find something. But anyway, observation 12 had a high and it had a large D fit. So it looks like it's not only remote, but it has some leverage too. I mean, some influence. Okay? And then there's something else called DF betas, which I didn't talk about yet today, but I'll talk about next time. And all these columns and so on, these are certain. The P stands for prime. It was a holdover. RP. There's a matrix R, which is given as this. It's given as C, the x prime x inverse times x prime. Okay. So R is C is a P by P matrix. This is a P by N matrix. P by N matrix. And this is a P by N matrix, so it has P rows, right, and N columns. But if we put it on its side, then the R prime has P columns. Okay? These are the P columns of that matrix. All right? 6 columns of that matrix. There's a 6 by 6 matrix running in here if I actually use that column of ones over here, right? The intercept. Okay? So x prime x has 6 columns. X prime x inverse has 6 columns. And x prime x, and if you take it r prime, which is x times c, that has 6 columns. All right? Anyway, those are the 6 columns. Those come into the computation. But here, you sort of determine there's numerical measures as to whether the betas were changed very much. Okay, and so according to this, in observation number 12, which was over here, observation number 12, apparently the first 3 betas, the intercept, beta 1 and beta 2, were affected by the influence of this point. Okay? And at another point, observation number 20, not only these last 4 betas were all affected. Even though in some sense, the Cook's D didn't come out that big. It never came out bigger than 1. Okay? So these maybe are a little bit more sensitive than the F betas J. So if you actually go ahead and you delete observation 12, I know we're over time now, which I did over here. I take observation 12 out and I actually looked at the full data set versus the subset data set. I like to see whether the first 3 coefficients are affected. Well, it looks like they actually are. And the last 3, well, not as much. It looks like the body was also affected a little bit, but not according to the cutoffs. Okay? And the last 2 weren't affected very much at all. So it seems the measures seem to work on that particular example. So you take the point out and see what's going on. And after that, what do you do with it? I don't know. Okay, you point out that it's an influential point. So then you just flag the influential points and you decide, based on some other criteria, whether, you should change the model. To put in some other kind of effects to try to affect for the influence or not. Okay. All right. So those are your diagnostic measures. Thank you for the time, extra time. And any comments about the exam? We still have tomorrow, right?
Some questions.
Get some questions?
I'll talk to you after.
Could you? Yeah, you want to just talk afterwards,
Yeah,
and
they're pretty brief.
we'll try to make them public on tomorrow.
Okay.
All right. So tomorrow's one of the last days to make things public. So please bring your questions about the exam.
And Monday?
Monday, there's still possibilities, and they'll be public via the recording. Okay.